Okay, welcome. This is New England Dynamics and Number Theory seminar. In fact, it's the last meeting of spring 2025. And we're happy to have Emilio Corso telling us something interesting about higher rank Furstenberg slicing. Here you go, Emilio.
Yeah, thank you very much, Dima, for the introduction, and thank you to the organizers for the invitation. I'm glad to be back. I apologize for not having been able to follow this seminar more consistently this semester, but I was teaching at 12 on Tuesdays, so I couldn't join. This is a dynamics and number theory seminar, but actually I would say that the main result I'm going to present today perhaps fits more squarely within the confines of fractal geometry, which I know is of interest to the audience here. But it's actually closely interwoven with some aspects of dynamics, specifically rigidity of high rank abelian actions, and some number theory also in its perhaps one of its most elementary incarnations, namely expansions of real numbers in integer bases. So the story here starts with the pioneering work of Furstenberg dating from the 60s on semigroups of endomorphisms of the one-dimensional torus. So let me set the stage first. So the ambient dynamics takes place on the torus, one-dimensional torus, R mod Z. And for every integer a, I have the standard endomorphism, which is given by multiplication by a on the torus. So x goes to a times x. And we all know that each of these maps taken on its own has an extremely rich chaotic behavior, admits many closed invariant sets, admits many ergodic invariant measures, to the point where actually classifying them all is virtually out of reach. But the crucial insight of Furstenberg was that if you consider now two different maps, and generally different maps, then some rigidity phenomena starts to appear. So let's consider A and B multiplicatively independent. Namely, they're not the same in disguise. That is, they're not powers of the same integer, multiplicatively independent. The shortest way to formulate this condition is that the ratio of the logs is irrational. And let's consider closed invariant sets under times A and times B separately. So I consider AB subsets of the torus, which are closed, and respectively TA and TB invariant. Where here invariance, it suffices to assume it in the weakest possible sense of forward invariance. Namely, the images contained in themselves. What can we say about the relation between A and B? Now, this is closely connected since multiplication by A on the torus encodes the base A expansion of a real number saying 0, 1. Furstenberg was led to a series of conjectures which aim to capture the heuristic principle that expansions in multiplicatively independent bases should be totally unrelated. And in particular, we expect sets which are closed and invariant under multiplicatively independent dynamics to be unrelated or to share no common structure whatsoever. So the first question one might ask about A and B to check whether they can have some common structure is, well, can they be equal? So what can we say about the case? And that's, of course, the first pioneering result of Furstenberg himself, what can we say if A and B are the same? So if we have a jointly invariant set, closed set, and that's very famous theorem of Furstenberg in 1967, that if A is equal to B, then either there are trivial invariant sets, which are, for instance, finite collections of rational points. So then either A is finite, and in which case it is contained in Q mod Z, consists only of rational points, or it is everything. It's a full ambient space. So extreme rigidity, in that sense, for jointly invariant sets, there are very few of them. And even if the focus of the talk will be on sets, it would be remiss not to mention one of the most well-known open conjectures in dynamics, perhaps, which is the measure theoretic analog of this, which is again due to Furstenberg, that if you have mu is a TA TB invariant, so invariant and ergodic under both maps. Well, actually, invariant under both maps and ergodic means that every set which is essentially invariant under both maps is trivial, measured theoretically, and ergodic. Or a probability measure. Then either mu is finitely supported, which can surely happen. For instance, the Dirac mass at 0 certainly satisfies this condition. Mu is finitely supported on finitely many rational points. Or mu is the Haar measure on T. And the best progress towards this conjecture is perhaps Rudolph-Johnson theorem, which proves the conjecture under the assumption that mu has positive entropy under one of the maps of the semigroup generated by times A and times B, in which case, if there is this positive entropy assumption, then the measure has to be necessarily Haar. And this, both the topological rigidity result of Furstenberg and the measure theoretic conjecture really sparked, can be seen as really initiating this vast program of studying rigidity of higher rank actions in homogeneous dynamics and beyond. I won't have anything to say about measures in this talk. The focus will be, I'm sorry, is there any question? Okay. So I won't have anything to say about measures. The focus will just be on sets, but of course, the conjecture is so famous that it really deserves mentioning. Back to sets. So now, okay, Furstenberg result addresses the case of A equal to B. What if A and B are now arbitrary and invariant under the two maps separately? Well, that's the subject of what is known as Furstenberg intersection conjecture, which is now a theorem, but let me just go through the history. So it started as a conjecture, which is one of many rigidity conjectures of Furstenberg's, perhaps more geometric in spirit compared to the topological rigidity result, but still aiming at capturing exactly the same principle I alluded to earlier. So this, I think, appeared really in print in 1970. That if you look now, a way to measure how much structure they share, A and B, invariant under times A and times B respectively, is to look at their intersection. What can we say about the intersection of the two sets? And we expect it to be as small as possible. And the way to measure the size of an intersection here is using some notion of dimension taken from fractal geometry, the most widely adopted one being house of dimension. So let me state it in terms of the house of dimension. Even though for these sets, all notions of dimensions that we know actually turned out to coincide for invariants, for closed invariant sets. But let me use the house of dimension for convenience. So the conjecture is that if you look at the intersection, it should be as small as possible, given the combinatorial data of the problem. And so in terms of the house of dimension, if you think about the what would be the analogous formula for the dimension of the intersection of linear subspaces, then should be the sum of the dimensions minus the dimension of the subspaces generated by the union. Now here the analog would be, so the maximal drop is, so this intersection is small as possible if the sum of A and B, the sum set of A and B is as large as possible in dimension theoretic terms, meaning if it has dimension 1. And so actually the conjecture is precisely this. This should be at most the sum of the dimensions minus 1. So maximal drop given the combinatorial constraints, except that this quantity can be a priori negative, so you take the supremum with 0. So if the sum is smaller than 1, then the intersection has dimension 0. And if the sum is larger than 1, then the dimension is the sum minus 1. The dimension of the intersection is the sum minus 1. Notice that if you apply this is actually stronger than the topological rigidity result, because if you apply this to A equal to B, then what you get automatically is that the dimension of A is either 0 or 1, if A is equal to B. And for invariant sets under these dynamics, it is not so hard to show that dimension 0 implies being finite under this joint invariance assumption, and dimension 1 actually implies being everything. So in that sense, it is stronger. Now, this conjecture, as I already said, is not a conjecture anymore. This is a theorem, which was first proven by Pablo Shmerkin in I mentioned the date in which it appears in print. It's an announced paper of 2019, but the result dates back a few years. And let me phrase a stronger result, which in Furstenberg's original terminology amounts to saying that the dynamics of times A and times B are strongly transverse, namely not only we can address intersections of the two sets, but also of isometric image, or even not just isometric, but affine images of one of the two. So the dimension actually of the intersection of A with any affine image of B, we're now here. So the result I'm stating, so this is, the upper bound is the same, but where now G is any affine bijection, where now, of course, I'm identifying implicitly the subsets of the torus for any affine bijection, where here the torus is identified canonically with 0, 1. And so the intersection conjecture actually resisted attempts for basically half a century until Pablo was able to provide a first proof. And after that, independently, this was also proven by, so subsequent proofs were provided by proofs, and let me emphasize, using completely different methods, more ergodic theoretic in nature, and closer in spirit to Furstenberg's original insights, different in spirit, in method. Appeared, and due to Meng the same year, and later the approach was considerably streamlined by Tim Austin in 2022. But again, both proofs are completely different in spirit, in nature, than what we are going to discuss today, which is an extension of Pablo's approach for his first proof of the intersection conjecture. So this is as much as we can say about two sets. But now the question arises naturally, what if I consider more sets? Three sets, for instance, invariant under, say, times 2 times 3 times 5. Is there an analog of this conjecture? And so now let's consider arbitrary finite collections of sets. Consider A1 up to AD closed, and with AI invariant under TAI. Now, under appropriate transversality assumptions under the for the AI, for the little AI, under appropriate transversality assumptions. By the way, let me just mention, going back to the intersection conjecture and to Shmerkin's theorem, that in general, one can only hope to attain a lower bound, an upper bound. Equality may fail simply because you can find A and B disjoint rather easily. But in this type of problem, it's only the upper bound that is really relevant. It can be a strict inequality, but what is really relevant is the upper bound. So under appropriate transversality assumptions on the TAI, we expect a generalization of the intersection conjecture, which is now a result theorem. On the TAI, we expect the analogous version so that the dimension, the Hausdorff dimension of the intersection, is bounded from above, this time by the supremum of the sum of the dimensions minus d minus 1. We have d sets, so it's we need to subtract d minus 1, but of course taking the supremum with 0. So this we expect by generalizing the case of d is equal to 2. And actually, a result in this direction was already proven a couple of years ago. Actually, by now 4 years ago, I would say, by Han Yu, who refined 2021, refined some aspects of the approach of Meng Wu in order to obtain the following result. So his condition, his transversality condition is the following. If the ratios log of A1 divided by log of AI, if this is a linearly independent family over Q, of course, for d is equal to 2, that's precisely saying that A1 and A2 are not commensurable, but multiplicatively independent. But in general, that's the condition that he needs, is a linearly independent family over Q. And if the sum of the dimensions is strictly smaller than d minus 1, so we are in the subcritical regime, then the Hausdorff dimension of the intersection is 0, and actually you can replace the AI by any affine images. So the dimension of G1, A1 intersected with GD, AD is 0 for all affine bijections. GI from R to R. This is certainly a generalization to finitely many sets, but there is an issue. Well, first of all, it only deals with the subcritical case where the sum of the dimensions is strictly less than d minus 1. But most importantly, there is no single concrete example of a finite collection of integers AI satisfying this condition. So no concrete example of A1, AD satisfying the condition is known, of course, beyond the case d is equal to 2. For instance, it is already unknown whether the condition is true for 2, 3, 5. Satisfying the condition is known for d at least 3, e.g. unknown for 2, 3, 5. It would be known, it is expected, of course, to be true, for instance, for 2, 3, 5, or any triple of prime numbers, or even more generally. It is expected to be true, but it...
Can you explain what exactly is not known?
Sure. The fact that the family of ratios log A1 divided by the log AI is linearly independent over Q.
Okay.
That's something that is not known, which is surprising at first, but notice that if you were to take the reverse, the opposite ratio, the inverse of that, log AI divided by log A1, then this is a rather trivial method. Then, of course, we know this. If you do the easy computations, we of course know that if you take the inverse ratios, then, for instance, they are certainly linearly independent for 235 or for any triple of coprime integers, for any family of coprime integers, but much more generally than that. Except that he really needs these inverse ratios, namely log A1 divided by log AI, and this is unknown.
Okay.
It would follow from a conjecture which is deemed to be inaccessible with current understanding of transcendental number theory, which is called Shmerkin's conjecture. This would follow.
Yeah, interesting.
Yes, indeed, it's very surprising. This would follow from Shmerkin's conjecture in transcendental number theory, which deals with the transcendence degree of extensions of the rationals generated by linearly independent complex numbers, Q linearly independent complex numbers, and their exponentials. This would follow from Shmerkin's conjecture. In transcendental number theory, let me just not mention directly the conjecture because it's not, instead let me mention directly the application to this problem. In transcendental number theory, as the conjecture implies, that this is the case, that log A1 divided by log AI is Q independent as soon as the inverse ratios are long independent, and that's a completely checkable condition. Log AI divided by log A1 is Q independent. So there was this issue with unused results of not being able to produce a single example beyond the case of two sets, which is one of the motivations behind our work with Pablo, extending this result by somehow dispensing with this condition, or actually assuming something less strong, and also dealing more generally with slices of products of such sets. Let me just now explain how this problem is connected to a well-known problem in fractal geometry, which is estimating the size of slices of fractal sets with subspaces. So intersections of the form which appear in Han Yun's result, G1, A1 intersected with GD, AD, where the GI are affine bijections, are up to by Lipschitz equivalent, let's say, intersections, slices of the product A1 times AD with lines, with affine lines in RD. Let me just give a concrete example in the case D is equal to 2. If you intersect A times B with a set of pairs of the form X, GX, X in R, which is the graph of an affine line, then up to projecting, this is equal to, up to projecting to A, up to projecting to the X coordinate, up to projecting to A, that's precisely A intersected with GB, G of B. And this generalizes immediately to the case of arbitrarily many maps. So the problem, we can understand the problem of such intersections by understanding slices of the product of such sets, invariant sets, with affine lines in RD. But of course, the moment we intersect with affine lines, we can more generally inquire about intersection with arbitrary subspaces. So we turn this problem, now we deal with this more general problem. More generally, we are interested in upper bounds for the Hausdorff dimension of the intersection of the product with V for any k-dimensional affine subspace V in RD, where, say, to avoid trivialities, we can, of course, assume that k is between 1 and d minus 1. This is, again, a well-known line of investigation in fractal geometry, which goes back at least to Marston's projection theorem. So there is a dual point of view. Slices are inverse images under orthogonal projections. And so let me start with the most famous result in this realm, which is Marston's projection theorem. Which dates from 1954. Actually, what I'm stating now is the generalization to arbitrary dimensions. So Marston proved the case of the plane of d is equal to 2 and intersections with lines. The generalization was due actually to Perti-Mattila in 1975, but people somehow refer normally in the community during talks to even to the generalization as Marston's projection theorem. So if you now take any Borel set, if E in RD is a Borel set, then if you look at the projection, the Hausdorff dimension of the projection, orthogonal projection of this Borel set onto, say, k-dimensional, actually, it will be more convenient to, in what follows here, to look at, to parameterize V above by the codimension instead of the dimension, for reasons which will become clear. So let me say D minus k dimension, I parameterize it by the codimension instead of the dimension, so that now for the projection, I can really talk about projection onto k-dimensional spaces. So if E is a Borel set, then you look at the orthogonal projections onto k-dimensional subspaces. Well, there is a natural upper bound for that. First of all, orthogonal projections are one Lipschitz maps. They cannot increase the Hausdorff dimension. So a natural upper bound is certainly the dimension of the space you are projecting to, k in this case. Sorry, actually, what I said refers to the natural upper bound with the Hausdorff dimension of E, and then there is a second upper bound, which is the dimension of the space. So the upper bound should be, actually the upper bound is, for every subspace, the infimum between the dimension of E and K, it's actually an equality almost everywhere. So then for almost every k-dimensional linear subspace, where almost every refers to the natural unique invariant Borel probability measures, Borel probability measure on the Grassmannian of k-dimensional spaces under the action of the orthogonal group, k-dimensional linear subspace W, we actually have equality, namely the dimension of the orthogonal projection onto W of E. This is orthogonal projection. Is the infimum, is the natural upper bound. Let's interpret this in the language of slices, which is most natural for our problem. Well, there is a version of Marston's projection theorem, which now by chance is called Marston's slicing theorem, perhaps just only slightly less celebrated than the projection version. What do we expect in view of the projection theorem? That's also the same paper. What do you expect in terms of slices? Well, the dimension of the slice of slices under orthogonal projections, which are nothing but dimensions of the intersections of E of an arbitrary Borel set E with affine subspaces of dimension D minus K, well, it should be bounded from above by the dimension of E minus the dimension of the projection. So we expect somehow an upper bound of which is the supremum between 0 and the difference between the dimension of E and K, except that the slicing theorem of Marston is slightly less strong compared to its projection theorem in the following sense. Then it deals with, so one needs to assume that we are in the supercritical regime, that the house of dimension is strictly bigger than K. And then the statement is that then actually for every k-dimensional linear subspace, W, we have the upper bound that we expect for the slice, which is E intersected with inverse image of the orthogonal projection under some element A, little a. So this is at most the supremum between the difference between the dimension of E and K and 0, which is nothing but the dimension of E minus the dimension of the projection, for almost every A, for Lebesgue, almost every A. In W. Again, here one cannot expect equality because simply you might have a bounded set that misses completely the fiber for sufficiently large A. So the upper bound is the only relevant that we are after, and it's the only one that you can actually attain. Not attain, that you can actually obtain, you can prove. So that's Marston's slicing theorem. Now it's these two theorems started a whole line of inquiry in fractal geometry, animated by the principle that if now you restrict the class of Borel sets you are looking at, then you should be able to have a better understanding of the set of exceptional parameters, namely those parameters both in the projection and the slicing theorem for which the result fails. In particular, if you look at fractal sets somehow, whatever fractal means, but sets generated in an arithmetic fashion or a dynamical fashion or with some strong geometric features, for instance, self-similar sets, then one should be able to understand the set of exceptions a lot more clearly, and in particular, there should be the only exceptions should be for really manifest reasons. And the result I'm going to shortly phrase fits into this program of research, because we are fully able for E being the product of invariant sets and the transversal toral endomorphisms, we're able to upgrade this really for every subspace, provided that one rules out the obvious exceptions. So let's go back now. These were the Master's theorem, which address the case of a general Borel set. Now back into the case of, so for E equal the product as above. Then how can we improve this? That's the theorem. Joined with Pablo. Problem 24. Well, actually, before stating the theorem, let me directly mention first a clear obstruction to this inequality here. If you take W, which is a coordinate subspace, namely if W is generated by vectors, by K vectors in the canonical basis of RD, then you have that the intersection of the product with pi W minus 1 of 0, well, this is simply the product of a subproduct. It's simply a subproduct. Can naturally be identified with a subproduct. So it's the product for I in I of the AI for some I of cardinality D minus K. So you're taking only some of those. And of course, the inequality can fail depending on the dimension, but then the house of dimension of this is precisely equal to the sum of the house of dimensions. And this can easily be larger than the upper bound, which is the upper bound provided by Marcel's slicing theorem. Depending on the nature of the AI themselves, on the house of dimension of the AI themselves. Can be larger. Strictly. Larger than the supremum between the house of dimension of E minus K and 0. So there are these obvious obstructions, but somehow, if you rule out taking slices with respect to coordinate subspaces, then you expect the inequality to hold, and that's indeed what we prove. And also, what are the transversality assumptions that we require on the maps? Now we dispense with Hanyu's uncheckable condition. Our condition is fully checkable. Namely, you only need the parameters little ai to be pairwise multiplicatively independent. So for instance, 2, 3, 5 certainly holds, but perhaps a little more surprisingly, even 2, 3, 6 is okay, for instance. So suppose A1, AD are pairwise multiplicatively independent. And the AI is above. Then for any D minus K dimensional affine subspace V such that the orthogonal complement such that V perp is not a coordinate subspace, we have the expected upper bound. So the Hausdorff dimension of the product intersected with V is at most the supremum between, okay, let me say S minus K and 0, when S from now on will denote the sum of the dimensions, also dimensions of the AI. A few words about this result. It holds more generally, just like Pablo's original proof of Furstenberg's intersection conjecture. It holds more generally for the upper Minkowski dimension, except that I will focus for the sake of illustration to the Hausdorff dimension. And well, we are actually able to provide a uniform version of this result. Namely, if you look at, say, for instance, how the upper Minkowski dimension is defined in terms of covering numbers or packing numbers, we are actually able to obtain some sort of uniform estimates depending on quantitative parameters by which we vary the subspace. But I won't get into this quantitative refinement. Let me just content myself with this qualitative statement and directly mention the corollary, which is the direct generalization of Furstenberg's intersection conjecture. So if you apply this to the case k is equal to d minus 1, you get intersection with lines. And so you get automatically that the dimension under the same assumptions on AI the Hausdorff dimension, okay, G1, A1 intersected with GD, AD is at most the supremum between the difference between the sum of the dimensions and d minus 1 and 0 for all affine bijections. GI, which improves upon unused result in two aspects. First of all, we also deal with the supercritical regime where the sum of the dimensions is larger than d minus 1. And also we relax considerably his assumption on the parameters AI governing the dynamics, in that we only require pairwise multiplicative independence. Like, for instance, again, 2, 3, 6 would be fine. Not only 2, 3, 5, but 2, 3, 6 is totally fine. So perhaps before saying a few words maybe about the proof, are there any questions about the statement? Or about what I said, whatever I said so far? Okay, so if there are no questions, let me say a few words about the proof, and then, of course, if time runs out, I'm certainly available to tell you more in the discussion session. So a proof outline. Well, we start with the first reduction, proof outline for the theorem. So we take intersection with arbitrary subspaces. There is a first reduction, which consists in the claim that it suffices to prove the inequality when the AI, capital AI, the sets, are not really any closed invariant sets, but are actually missing digit sets in base little AI. So it suffices to assume, to prove the theorem for AI missing digit set in base little ai, where missing digit, of course, means that I forbid a certain subset of the digits when I look at the base ai expansion of the real numbers. Natural generalization of the middle third counter set. Why is that? Well, using the symbolic coding of the dynamics, it's not so hard to show that, indeed, for arbitrary AI, closed invariant, again, using the symbolic coding, it's also hard to show that there exists, and for every epsilon, there exists a missing digit set. There is BI, which contains AI, and is a missing digit set. In base, well, not necessarily. If you really want to approximate it as close as possible, you have to allow for powers of AI. So in some base, but it's okay again. AI to the m for some m. Integer. Well, such that the Hausdorff dimension almost coincide. So the Hausdorff dimension of BI is at most the Hausdorff dimension of AI plus epsilon. So in dimension terms, you can really approximate closed invariant sets by missing digit counter sets. And for the purpose of that statement, using this claim, it's easy to reduce it to the case of missing digit counter sets. So that's the first reduction. From now on, the AI will be actually missing digit counter sets in base little AI. If you want to estimate fibers, size of fibers under Lipschitz maps, then there is a fairly elementary lemma, which, as usual in fractal geometry, reduces computational matters for dimensions of sets to measures, to dimension of measures supported by those sets. And the lemma in this case goes as follows. If X and Y are metric spaces, it's really an elementary lemma, but it's crucial for this approach, for the approach we are pursuing. Our metric spaces, say with X compact, and pi is a Lipschitz map. Well, suppose we have a measure mu, a probability measure. Suppose mu is a Borel probability measure. On X, such that for some fixed real parameters S and T, real 0 at most T at most S, we have that the mu measure of every ball, that's my notation for the closed ball in X centered at little x and of radius r, is at most r to the S. And the projected measure of every ball in Y, and sorry, that's the converse inequality. I want it to be at least, and this to be at most r to the T. And this holds for every, really, not for almost every, but really for every x in X, Y in Y, and every radius. Then for every Y, every fiber, the Hausdorff dimension of the fiber, p minus 1 of little y, is at most S minus T. Now let me walk you through the statement. What is this saying? Well, these conditions, this condition on mu says, if you're a little familiar with fractal geometry, in particular with Frostman lemma, this doesn't surprise you at all. This condition says that mu as somehow dimension at most S, Hausdorff dimension or any dimension you can imagine, at most S. Whereas this condition here says that the projection has, in a very strong uniform sense, Hausdorff dimension at least T. So if you imagine, you start with a measure on X whose dimension is at most S and projects to a measure whose dimension is at least t, then the fiber should be very small in dimension, namely the natural upper bound is the difference between the dimension of what you have in the domain and what you have in the target set, which is S minus t. Again, the proof of this lemma is two lines. Say you can even prove it not only for the Hausdorff dimension, perhaps it's easiest to prove it for the upper Minkowski dimension. You just write down the definition of the upper Minkowski dimension as the growth rate of packings, and you are, if you want to estimate packings, epsilon packings of each fiber, then you are automatically led to use these two inequalities. So it's really an elementary lemma, but it's again crucial for our approach. Because now we apply this lemma. Probably I should also conclude shortly, but of course I can tell you more after the talk. We apply this lemma to, well, of course, X is the product. Okay, it's not compact, but it sits inside a compact set. I just need X. I assumed X to be compact. The only relevant thing is to be totally bounded. And pi, well, the orthogonal projection onto the orthogonal complement onto V perp, where remember that V is the subspace we are intersecting with. And mu is the product of the natural Cantor-Lebesgue measures supported on the Mr. Cantor sets. Mu I is the Cantor-Lebesgue measure of maximal entropy, maximal dimension, however you want to characterize it, Cantor-Lebesgue measure on AI, for which everything is known because, and has been known for quite some time, because these sets, Mr. Cantor sets, are the nicest fractal objects you can imagine for them, and for the natural self-similar measures they support, everything is known. In particular, here S is really the S above, which is the sum of the dimensions. So the only thing that is left to examine is the T. What can we say about the T? So we need to examine. So the problem which we address and solve is examining the Frostman exponent T for the projection of such a product, for the projection of mu. And this proceeds by a complete understanding of the what is known as the LQ spectrum and LQ dimensions of such measures, which in turn relies on an inverse theorem for the LQ norm of convolutions of discrete measures on Euclidean spaces, which is a generalization of a well-known, well, a generalization, a refinement in certain aspects of a very well-known theorem in additive combinatorics, which is the Balog-Semeredi-Gowers theorem. Of course, I'm happy to tell you more in the question sessions. For the moment, let me just stop here. Thank you.
Okay, great. Well, let's thank Emilio.
Thank you very much.
Again, a round of applause, virtual or otherwise. And any questions? So maybe it's a big question, but the last sentence had too many big names and big words. Could you maybe decipher?
Of course. Yes. Yes, exactly.
How it is related to Semeredi-Gowers?
Yes, exactly. So yeah, let me try to do it's actually a tall order to say something about, to relate these big names to what's going on here in a short time, but I will try to be as concise as possible. So how is this related to additive combinatorics? So examining the Frostman exponent amounts to examining, so here you want really a uniform estimate here for every center and for every radius, which amounts, okay, we replace, it's typical procedure in fractal geometry, we replace disjoint balls with actually cubes of at a certain generation. So it amounts to understanding, we want to understand what is known as the L infinity dimension of the measure P of mu. Understand L infinity dimension P of mu which is defined as the limit as m tends to infinity of, you want to look at the exponential decay rate of the supremum of all measures of cubes of a certain, say, dyadic size. So it's the supremum. So exponential decay rate, so it's log of, the supremum, somehow the L infinity norm. The supremum over all cubes in the M, I will specify in a moment what is the M, is simply the dyadic partition of side length 2 to the minus m of pi mu q and exponential decay rate. So with m, we're here log, for simplicity, since I will look at dyadic partitions, it's log in base 2. And dm is the standard dyadic partition, so it's a set of all cubes of the form 2 to the minus m k plus 0, 1, where m is in ZD. Standard partition with cubes of side length 2 to the minus m. So once we have a lower bound for this, understand the lower bound for this outer dimension, then we have an upper bound for the Frostman exponent. Actually, we have a lower bound for the Frostman exponent, namely we have the upper bound that we want here. Except that we all know in analysis that there is a wider array of tools to estimating LQ dimensions for finite exponent Q compared to L infinity dimension. So we actually use the fact that this is the limit as Q tends to infinity of the corresponding LQ version, which is known as the LQ dimension of pi of mu, which is the limit when now you take LQ moments. So minus log of the sum pi mu q to the power q. And turns out that the right normalization here is by q minus 1 and then times m. So exponential decay rate of these q moments of the measure. Now, this is actually, now for the sake of illustration, let me just replace pi of mu with a homogeneous self-similar measure, because it's for pi of mu there are additional pieces of data that enter into the framework and will completely they will completely cloud the gist of the argument. So let's assume instead, for illustration, replace pi mu with some nu, which is, say, a homogeneous self-similar measure, so it really satisfies the natural self-similarity relation, pi I fi mu, where the fi, say on R, are contracting similarities. And P is a probability vector. Now, it turns out that such a measure, it's in the homogeneous case. So if the Fi have same contraction ratio, it's a convolution, it's an infinite convolution, have same contraction ratio, then you can express this as an infinite convolution product of a certain measure, a certain finitely supported measure, which I'll denote delta 0, and I'll specify in a moment, rescaled by common contraction ratio, say lambda, in 0, 1. That's lambda to the n. Where this measure here is simply you place weights pi in the translation vectors, which I should probably call bi because ai are already taken, where here the map fix is really lambda x plus ai plus bi. So it's a it's a one-line exercise to show that this infinite convolution actually satisfies the self-similarity relation, and hence by uniqueness, which is an abstract result, you get this expression. So you're looking at really, we want to understand LQ dimensions of such infinite convolution products. Now it turns out that if you look at the scale mn, where we're looking at the adic scale, which have to be squared with the fact that here we are scaling by parameter lambda. But if you have mn where m2 to the minus mn is approximately of the same order of lambda to the n, is as close as possible lambda to the n, then it's not surprising that if you look at these LQ moments for, I call it nu, sorry, at scale, at this dyadic scale, which matches roughly lambda to the n, then what is actually only relevant up to some uniform multiplicative constant is the discrete measure nu n, where what is nu n? Nu n is the discrete measure that you obtain by simply taking the convolution of the first n factors, lambda I delta 0. So you forget about what happens everything from scale r to the n onwards. Why is this almost true? Because your measure nu is the convolution of this nu n times a measure which lives at scale lambda to the n. And if you are looking at LQ moments at that precise scale, then you're only shifting the support somehow, but these quantities are not affected up to some bounded uniform factor. So if you accept this, then the point is that now if you look at these LQ norms for these discrete measures, then there is a natural upper bound. And there is a natural upper bound, namely the limit. Sorry, there is a natural, well, there is an upper bound for the corresponding dimension. The limit as n tends to infinity of minus log of this LQ moment here. There is a combinatorial upper bound, which is divided by, okay, q minus 1m, the LQ dimension, which turns out to be the log of the LQ norm of the probability vector p divided by q minus 1 log lambda. So a combinatorial upper bound which only depends on the parameters of your iterated function system. But the point is that we actually get equality here under some assumptions, which are satisfied in particular by these projections of these products. And getting equality relies on the fact, which is, I can call an LQ flattening result, that if you take the LQ norm of, say, the measure nu, discretized at scale m, so this is simply the discretized 2 to the m minus m discretization of nu, where you simply place all the mass in a cube to, say, one of its corners, say the bottom left-hand corner. So it's a discrete measure now, 2 to the minus m discretization of nu. Now, if you take the convolution with any measure, rho, now Young inequality, and you look at the LQ norm, now Young inequality will tell you that this is at most, the LQ norm of nu, the 2 to the minus m discretization of nu. But actually what we prove is that if there is some randomness for rho, which we express by saying that the Q moment of rho is some 2 to the minus sigma m, then this is less, you actually get an improvement upon Young. This is 2 to the minus how should I say this? Okay, dim q nu plus epsilon, so you get a strict improvement upon Young, where epsilon here doesn't depend on anything apart from sigma. For every sigma, if you have some randomness on, if you convolve, of course, if you convolve with rho being Dirac, then you cannot expect to have this improvement. But the moment you have some randomness for rho, for your finitely supported measure, it's not really a Dirac mass at scale 2 to the minus m, then actually the convolution really smoothens out the two factors. You get a strict gain compared to Young's inequality. And this strict gain, which is the crucial argument which leads to this equality here, under some, of course, some additional work, but that's where the additive combinatories comes into the picture, because now the inverse theorem comes into the picture, telling that if this were not the case, if you didn't have now this inequality, so if Young inequality now for two completely arbitrary measures, discrete measures, mu and nu, if Young's inequality for them is close to equality on an exponential scale, then actually the two measures must have a well-defined multifractal structure where at each step of the multiscale subdivision, either one of the factors resembles closely a Dirac mass, or the other factor is almost uniform. Because of course, this equality is again, and this inequality is again an equality, and you cannot expect to gain anything if nu, say, was Lebesgue. Then you already have the maximal possible LQ dimension. You cannot improve upon Young. And somehow, if you are close to the inequality, then this inverse theorem, which was proven separately by Pablo Shmerkin, tells you that actually you have a multi-scale decomposition. And at each scale, either you have that rho is almost Dirac, or the other factor is almost the uniform measure. And again, this, if you look at the case Q of equal to 2 of this statement that I just said, just verbally, and if you look at discrete measures nu1 and nu2, which are uniform measures on finite sets, this inverse theorem that I've just mentioned are uniform measures on finite sets A and B, then the inverse theorem is precisely a reformulation of the Balog-Tsemeredi-Gowers theorem in additive combinatorics that tells you that if you have two finite sets now in RD, or actually in any abelian group, two finite sets AB whose additive energy, which somehow measures the amount of overlaps among all possible sums of elements of A and B, if this is close, if the additive energy of the sum of the two sets A and B is close to its natural upper bound in terms of the size of the cardinalities of A and B, then the sets A and B have a very peculiar multi-scale structure where one of the two is almost a K-approximate subgroup, has some algebraic structure, and the other one sits inside one of the translates of this subgroup. So I know this was very, very short, but I try to do my best to illustrate somehow, at least vaguely, where additive combinatorics comes into the picture.
Okay, that's great. Thank you. Any other questions? Well, let me ask maybe not a well thought out question, but if you have two subsets of the two-dimensional torus, and each of them is invariant under some hyperbolic toral automorphism, which don't talk to each other.
Yeah.
Can anyone see?
Yeah, so that's a very, very good question. So if you take hyperbolic toral automorphisms,
Or
honestly,
expanding maps or something.
yeah, exactly. Yes, exactly. This framework would address actually the expanding map, which is you multiply by A on each coordinate. So you look at the diagonal multiplication by A. This fits squarely within this framework. And that's a very good question. This was one of our motivation, except that, say, for the two-dimensional torus, you look at times 2 times 3, then what happens is mysterious already on the topological level. Mm-hmm. For instance, it is known, there was a series of counterexamples provided by François Moncourin in 2010 to a series of conjectures of Margulis, that already the topological rigidity result of Furstenberg fails. Namely, if you take, say, times 2 times 3, on a torus of sufficiently high dimension, if I remember correctly, for times 2 times 3, you need at least 6-dimensional torus, then you can actually cook up an orbit which is not dense and does not sit inside any subtorus. So its closure is not homogeneous. So the natural expectation for the higher dimensional version of Furstenberg in this case fails. Now for times 2 times 3, what happens between dimension 2 and dimension 5 is almost completely mysterious. There was a result of Han Yu, a name which I've already mentioned in the course of this talk, who proved that for the 2-dimensional torus, say, if you add times 5, if you look at times 2 times 3 times 5, then you have rigidity for orbit closures. But somehow his argument is not able to understand, he needs to add one map in dimension 2. And actually, if you increase the dimension, then you need to add sufficiently many maps to understand. You need to enlarge your subgroup. For times 2 times 3 in the 2-dimensional torus, the topological rigidity is unknown, and even, of course, even less is known if you take now two sets which are invariant under two separate maps. Mm-hmm. What we believe with Pablo is that, but we haven't written down the details at the moment, what we believe is that what we can get using our approach is, at best, a dimension drop. Namely, that if you take A and B, which are not included in the, say, contained in the same subtorus, invariant subtorus, then the house of dimension of the intersection is strictly smaller than the infimum of the house of dimension of the two, which is, of course, far weaker than what you can get in the one-dimensional torus. But again, already the picture for jointly invariant sets is completely, is almost completely open.
Mm-hmm.
But yeah, thank you for the question. That's a very relevant. It was one of the motivations of our work, certainly.
Yeah, that's very interesting.
Yeah.
So any quick questions at the end? If not, let's thank Emilio again. And with this, let's conclude this talk and our program for the semester.